Our next speaker is Jeremy Bernstein. Are you here, Jeremy?
I am.
I see you.
Can you hear me?
I see you. Yeah. So why don't you share your screen? Our next speaker is Jeremy from Caltech, and he's here to speak about computing the typical information content of infinitely wide neural networks. Take it away, Jeremy.
Great.
Looks great.
Can you hear me and can you see
Everything
this?
perfect.
Okay, amazing. Yeah, thanks. That was a really interesting talk, and yeah, it's a pleasure to be here. So yeah, so this is a work about generalization theory and about the information content of a classifier. So the idea is that we have a training set, and we have a classifier like a neural network, which may, be really overparameterized. And what we're interested in is, through the course of learning, how many bits of information pass from the training set into the classifier, and can we count that? Can we quantify that? Now, this isn't just like a curious question, but it relates to generalization theory through the framework called PAC-Bayes, which is a type of generalization theory. So I want to start by making some claims, which hopefully you'll get a sense of throughout the talk. But the first claim is that PAC-Bayes is just different to VC theory. It works in a different way. The PAC-Bayes bounds depend on the training data distribution. So it's not like uniform convergence like VC theory. The bounds are data dependent. The bounds, the generalization bounds don't involve the number of parameters in the model, which is also good. And in the case of neural networks, the bounds actually depend on the neural architecture, which is something that we really want. And the contribution of our contribution was to really bring the PAC-Bayes bounds into like an analytical form for neural networks. So we think that they're ready for like lots of analytical study. Okay, so these are just claims at this point. So I'm going to introduce PAC-Bayes on this slide. So the idea of what this theory is it says that you have a classifier, and it has a weight space, which I illustrate with this box. And what the weight space means is that a point in weight space is a weight vector. And then we consider something else, which is a subset of weight space, which is the solution space. And what we mean by solution space is that you have a supervised data, you have a training data set, and the solution space are those weight vectors that make no misclassification on the training set. So they attain 0% training error. 0% train error. Okay. So there's a really important quantity in PAC-Bayes bounds, which I'm going to call P, which is the probability that you randomly sample a weight vector and that it lies in the solution space. So it's the probability of randomly sampling a solution. And you can see from this picture that it's equal to the volume of solution space divided by the volume of weight space. So P depends on these kind of global properties of solution space and weight space. And the next claim is that P tells you the information content of a typical solution. So to see that, there's a thought experiment, and it says, imagine randomly sampling weight vectors until you find a solution by chance. To communicate to someone as the solution, you can just tell them the number of draws that it takes, because they can take the same random seed, they can rerun the same random sampling, and they can recover the same solution. So if you, basic probability says that the number of draws goes like 1 over P. And this implies that you can communicate that number of draws in log 1 over P bits. So that's the argument. The cost of communicating a randomly found solution from within the solution space is log 1 over P. So that's the relation to information content. You can communicate a random solution in log 1 over P bits. The relation to generalization theory is given by PAC-Bayes, which says a simple form of the bound is that the average test error of all solutions. So remember that solutions get 0% train error, but not 0% test error. So you imagine integrating the test, you imagine integrating over the whole solution space and averaging the test error over all those solutions. And Pac-Bay says that that average test error is bounded by log 1 over p divided by the number of training data points. This is a slight, I'm neglecting the fact that this is a pack bound, so I'm just neglecting that issue, but really this bound holds with high probability over the training set, but I'm just neglecting that because it's not needed the first time you see it. But the point is that the average test error is bounded by the number of bits needed to describe a solution divided by the number of training data points. And there's some things make this a good fit for deep learning. Like notice that it's not saying that there are no solutions that overfit. It's just saying that on average, the solutions would get low generalization error. Okay, and the main question that you should have at this point is like, well, how do you compute log 1 over p for a neural network? Like it depends on global things like global volume of weight space, global volume of solutions. Okay, so that's what we're going to look at now. So the first idea is that if we move from weight space to function space, computing p is going to be easier. So instead of measuring solutions in weight space, which is complicated and we don't understand, we move to function space where things become simple. So the technical tool for doing that is the neural network Gaussian process correspondence. So I'm going to introduce that using an example because, well, anyway. So what the example is I have 4 inputs, input 1, input 2, input 3, and input 4, and they're just trucks, images of trucks with varying amounts of noise. And the setup here is that I took a MLP, a multi-layer perceptron with 3 layers. The width of the hidden layer is 1,000, and it has 1 output unit. And what I do to generate these scatter plots is I sample lots and lots of random networks. And for every, by sampling random weight matrices, and for every random network, I plot the outputs for a pair of images. Let's say this scatter plot plots the output for image 1 against image 2 for lots and lots of random networks. And there's two observations jump out to you. Like the first is that the network outputs look Gaussian under random sampling of the weights. And the second is that the correlation of the Gaussian seems to match the degree of similarity between the inputs. But what does this have to do with, you know, computing log 1 over p or computing 1 over p, that quantity that we were interested in? So imagine that we're doing classification between trucks, which get labeled +1, and like noise, which gets labeled -1. Well, if you think about it, we're interested in the functions which are positive on trucks and they're negative on noisy images. So what we're really saying is that we're interested in all the solutions to this classification problem, all the functions which lie in this quadrant of function space. And if we had more inputs rather than a quadrant of function space, it would be an orthant, which is the higher dimensional generalization of a quadrant. So the idea is that in weight space, you know, the geometry of the solution space is really complicated, but in function space, it's an orthant. And in particular, we're interested in what's the probability that we sample we sample a random Gaussian vector and that it lies in a particular orthant. So that's like we've like reduced the mathematical problem to like estimating a Gaussian orthant probability. So that like identification with orthant probabilities is like our first contribution. And then the second is like providing some tools to like analytically deal with orthant probabilities. So I'm going to introduce that now. So again, like we've abstracted the problem of this P that we're interested in, the probability of randomly sampling a solution can be abstracted to, you know, you sample a Z from a multivariate Gaussian distribution. What's the probability that the sign of Z matches a binary reference vector C? The trouble is that in high dimensional Gaussians, it's going to, if you try and estimate this directly, it's going to take an exponential amount of time before you even hit the orthant that you care about. So we derived this estimator, which has nicer properties. So we break P up into a few terms. The first term is just the orthant probability of an isotropic Gaussian, which is just 1 divided by the number of orthants. And then there's a correction factor because of the fact that the covariance is anisotropic. And this is an expectation over Z from a standard normal of this complicated thing. And the thing I want to point out is just that this is the isotropic term for an isotropic Gaussian. And if you look at the matrix, which is appearing here, this is a measure of anisotropy because it's comparing the difference between a rescaled inverse covariance and the identity. So like when the covariance is just proportional to the identity, that term disappears. And then the next thing we did is that we actually derived the lower bound on the orthant probability. And for the details of that, you can see the paper, but the point is that it's derived by just applying Jensen's inequality. So to reiterate, our contribution here is really like identifying the geometric structure of solution space in function space and deriving these analytical results. And I'll go over prior work at the end, but this is where we've gone beyond prior work. Okay, so now we can actually put all the pieces together. So this is how the way we derive generalization bounds for overparameterized neural networks. So we take a training set with like capital N data points, and the Y's are binary labels. So the labels are plus or minus 1. For every pair of training inputs, we compute the correlation of the network output under random sampling of the weights. So we take in xi and input xj, and we compute the correlation of network outputs for this pair of inputs. The next step is we take that covariance matrix and we compute the orthant probability of the binary class label vector under that Gaussian using the techniques that we just introduced on the previous slide. And then the final step is we get P, we compare log 1 over P with the number of data points. And by Peck Bayes, if log 1 over P is smaller than the number of data points, then we should generalize on average. Okay, I just want to draw your attention to several features of this process. So notice that the training data set is essential to this process. So it depends on the data, it depends on the correlations between data points induced by the network. It also depends on the network architecture because F is the neural network and that's appearing in this process. So these bounds are architecture dependent. And then again, like nothing about this process says anything about the number of parameters in the network. Like the number of parameters doesn't matter. And we've actually, to use this neural network Gaussian process, we've actually taken the number of parameters to infinity. You could still do this process for things at finite width. It's just then technically for the results to be correct, exactly, it has to be infinite width. Okay. So we have this process. The last thing we did is we tested it experimentally. So the first finding is that even for infinitely overparameterized networks, this gives you non-vacuous generalization bounds. So the setup here is we have a binary classification problem, and we're plotting test error against the size of the training set. And because it's binary classification, chance performance is at 50%. So that's what the blue line shows you. And what the green and the purple curve are showing is the green curve is the performance of our bound on orthant probabilities converted into log 1 over P. And the purple curve is the performance of our estimator. And then the curves at the bottom are the empirical result for actually training a neural network at finite width. So you can see that the bounds are better than chance, they're non-vacuous, even though you only have a few hundred data points, but you have an infinite number of parameters. And also they do correctly bound the empirical training performance. I should say that the task here is doing parity classification of MNIST. So is an MNIST image even or odd? Okay, the next thing we wanted to do is try something a bit more interesting. So we compared the bounds across different data sets, and data sets of varying complexity. So that's what this plot shows. The axes are the same. It's test error against size of the data set. And the key point of this slide is that the bounds, the ordering of the bounds reflects the complexity of the data set. So the orange curve is random labels, meaning you take MNIST images, but you give them random binary labels. And we found that the bounds is worse than chance, meaning that, which is good because the task is impossible. It's impossible to learn from random labels, and the bound becomes vacuous. The purple curve is the same setup from the previous slide. So it's doing parity classification of MNIST. And the green curve is MNIST, but restricted to only zeros and ones. So we threw away all the other classes, which if you think about it, makes the classification problem easier because there's less diversity in the data set. And so the point of this slide is that the ordering of the bounds reflected the complexity of the data set. And the final thing we did on the next slide is we wanted to fix the data set, but vary the architecture. So this is varying the architecture. And the takeaway of this slide is that the bounds actually predict which architecture generalizes better, at least in this case. So the green curves show a depth 2 MLP, and the purple curves show a depth 7 MLP. And the solid lines are the performance of the bounds, and the dashed lines are the performance of the empirical, like we actually train the network. And what you see is that the ordering of the bounds say that depth 7 is better than depth 2, and the empirical result we found that depth 7 was better than depth 2 for this task. So okay, I just wanted to finish by saying that these ideas have a really rich history, and if you're interested to dig in, there's some references here. I want to draw attention to this group in Oxford who've really been pursuing this connection between NNGP, like neural network Gaussian processes, and PAC-Bayes. Our contribution that goes beyond that work is actually tying things together analytically. So you'll see that they use a lot of Gaussian process approximations, whereas we've identified this structure of orthant probabilities and derived some analytical results on orthant probabilities. But it has a really interesting history, this area. This was joint work with my advisor Yisong at Caltech. So what I've put on this slide is a link to a GitHub repository, which has the code and also a link to an extended version of the paper. So if you're interested to dig in more, that's there. And also, if I don't answer any of the questions now, I put my email address and feel free to reach out to me. But just to give you the takeaways, PAC-Bayes gives you generalization bounds which don't depend on number of parameters, do depend on the data set, and do depend on the network architecture. So I think it's quite an exciting area. Anyway, thanks. Yeah, thanks for listening.
Thank you, Jeremy. Really interesting. Yeah, really interesting talk. Let's thank Jeremy in our electronic means. And congratulations for finishing in exactly 20 minutes. So thank you so much. Yeah, really interesting talk. We have some questions, and I believe that Lorenzo and Reinhard are already cleared to speak. And so let's start with Lorenzo.
Hey, yeah, great talk. I was just curious about something I didn't understand. So why do you guys focus on the orthant, I guess, instead of the other quadrants? What's the significance of that?
So by orthant, I mean a high dimensional generalization of an orthant. But what it means is it's the region of function space where the outputs of the network are consistent with the labels of the training data. So this is because we're deriving generalization bounds, assuming that the classifier exactly fit the training labels. But if you wanted to generalize these bounds to the case where the training error is like not 0%, but say 5%, then you would actually need to start combining different orthants. But
I see.
yeah, it's the region of function space that is consistent with the training labels just is an orthant in the case of binary classification.
Thank you.
Okay, thanks, Lorenzo, for the question. Reinhard, question.
Hi, yeah. So I was wondering, can the quantities in those bounds be computed or estimated in some practical setup, like say, for example, CIFAR 10 classification with a ConvNet or something like that, to see whether they predict the generalization performance in practice?
Right. Yeah, so the answer is that they can. And this is something that this group in Oxford, so there's a professor called Ard Lewis and his grad students have been doing, but they use GP approximations to compute these quantities. But yeah, they find that it does scale. This infinite width technique does scale to like interesting architectures. Another point to mention is, I think you say, is infinite width required? Oh, is it to linearize the model or for another reason? It's the reason we require infinite width is not to linearize the model, and we're not doing like NTK stuff. The reason we have it is because it just makes the function space Gaussian. So we're interested in the prior on functions. We're not involved in anything. We're not saying anything about training algorithms. We're just purely studying the function space. To do this technique in finite width, this is actually, there's a paper by Dan Roy and Carolina Zwigait, or I'm not sure how to pronounce her name, but basically their paper called Non-Vacuous Generalization Bounds is doing this technique for finite width networks. But the thing, if you do it for finite width networks, it's very hard to get analytical results like the ones that we got. So they have a computational approach, and it purely explores local. So the nice thing in infinite width is that you can characterize global properties of the function space, including the global volume of solutions. What they do with finite width is they draw a small ball around the initialization, and they compute the volume of solutions within that ball that lies around the initialization. So it's a computational approach that doesn't have this analytical insight that we give, but it works for finite width networks and gives you non-vacuous generalization bounds. But it's messier. Like basically, you don't even know how large that ball around the initialization should be. So the approach becomes quite messy for that reason. Whereas this is very elegant, or in my opinion, it's very simple, but it relies on the infinite width assumption to make it simple.
Okay, very, very interesting. Many thanks.
Yeah, thanks, Reinhard. We have time for one last question from Jasper.
So based on this, are there any insights on how to come up with better training data sets? Any particular properties of training data sets that could make generalization better? Yeah, this is a great point that I didn't really have time to get into this, but the takeaway is that it's easier to generalize if the thing that allows for generalization is that the correlations between the data at the network outputs for things within the same class are sort of better correlated than across classes. So the role of architecture is to sort of induce this kind of good correlation structure between classes at the network output. And if you could work out a way to featureize your data such that that was already the case even without using a network, then it would be easier to learn and you would require fewer samples to learn. And it's sort of intuitive, because if the correlations in the data are already strong between things in the same class and are weak between things in different classes, it's almost like you already solved the classification problem. But that's this does have something to say about both like what the role of a network architecture should be, and also about the correlation structure that you would like to have in your training data.
Yeah, it makes a lot of sense.
Okay, thank you. Yeah, thanks so much, Jeremy. Really great talk. Thanks so much for coming. And let's thank Jeremy one more time.
Thank you.
And yeah, thanks so much.